study 10th Standard ICSE Physics, Chapter 11, Calorimetry, Exercise A, Numericals. These numericals are based on the principle of calorimetry. Mark the following sums as IMP, the 6th, the 10th, these two sums. Let's start with the third sum. A piece of iron of mass 2 kg has a heat capacity, not specific heat capacity, but heat capacity of 966 joule per Kelvin. Find first the heat energy needed to warm it by 15 degrees Celsius and its specific heat capacity in SI unit. What is the meaning of heat capacity? Well, it's the amount of heat required to raise the temperature of any substance by 1 degree Celsius or by 1 Kelvin. So it depends on the mass of the object. But in the formula, there is no mass variable. On the other hand, specific heat capacity does not depend on the mass of the object, and hence in its formula, there is mass. So Roman number 1, total heat is equal to heat capacity into temperature. Remember this formula. There is another formula which is total heat energy is equal to mass into specific heat capacity into change in temperature, which can be an increase in temperature or decrease in temperature. But mass into specific heat capacity is nothing but heat capacity, which is C dash. So you see, these two formulae are very similar. So the heat capacity is given, and even the change in temperature, in fact the increase in temperature is given. Whether it is in degrees Celsius or Kelvin doesn't matter, because it is the change in temperature. And it's in kg, so the SI unit is 14,490 joule. Next, how to find specific heat capacity? Well, as I said, mass into specific heat capacity is heat capacity. So that means if I send mass down, specific heat capacity is heat capacity upon mass. Substitute the values and we get the answer in joule per kg per Kelvin. We could have written it as per degree Celsius as well, but in this sum, since they've mentioned right in SI unit, write Kelvin and not degree Celsius. We could have written this like this as well. Joule, kg inverse, Kelvin inverse, which is the same thing. But if you're putting the inverse sign, please don't put the upon sign as well. Now in the 6th sum, which is IMP, find the time taken by a 500 watt heater. So that's the power. And we know that power is equal to work upon time. To raise the temperature of 50 kg of a material of specific heat capacity, blah, from 18 to 38 degrees Celsius. Assuming that there is no loss of heat. First of all, what is the total heat provided by the heater? The heat energy in joule. What is the formula for that? Well, the formula is Q is equal to mc delta T. Mass is given. Specific heat capacity is also given. Check, are the units same? Everything is in SI units? Yes, it is. And the change in temperature is 20 degrees Celsius. So the total heat provided is 960,000 joule. That is 960,000 joule of heat energy is being provided by the heater. But the power of the heater is 500 watt. What does that mean? 500 watt means that 500 joule of heat is given per second. You see here the work done by the heater is equal to the heat given by the heater. So instead of work in the formula, we can write heat. Of course, we are assuming here that no loss of energy takes place. So instead of writing power is equal to work upon time, in this chapter, we will write power is equal to total heat upon time. The power's value is given 500 watt. Heat's value we found out. So we substitute the values and we get the value of time in seconds. 1920 seconds is too big a value to be described in seconds. So let's divide it by 60 to get 32 minutes as the final answer. Now 8th sum is similar. There is half a kg of lemon squash at 30 degrees Celsius, which is placed in the refrigerator to cool it. We can remove heat at an average rate of 30 joule per second using the refrigerator. If you notice, joule per second is another way of writing watt. So this is basically the power of the refrigerator. 30 joules every second, or 30 watt. How long will it take? That means we have to find the time to cool the lemon squash to 5 degrees Celsius. And the specific heat capacity of squash is given. Surprisingly, it is equal to that of water. So again, what is the total heat to be removed from the lemon squash to cool it? Well, it's mc delta T, mass is given. C's value is given as 4,200 into 30 minus 5, that is 25 degrees Celsius. And then on multiplying, we get 52,500 joule. Do not just copy from here. Do the multiplication on your own. You need the practice of that. So this is the total heat energy. Now, power is equal to heat upon time. Power is given. It was 30 watt. Heat, we have found out. So we can substitute and get the value of time, which is 1,750 seconds. But let's convert it into minutes. How do we do that? Will we divide this by 60? Do not try to reduce it. Whenever you are converting seconds into minutes, do not cut 00 and cut it further. Don't do that. Just directly use the normal division method to get the answer. Whatever quotient you get is the minutes, that is 29 minutes, and whatever remainder is left is 10 seconds. If you do a normal reduction method, you will get the answer in decimal, which is not acceptable as far as time is concerned. Because if they say 29.23 minutes, it doesn't make sense because we don't know how many seconds apart from 29 minutes will be required. Next, the ninth sum. A mass of 50 gram of a certain metal at 150 degrees Celsius, quite hot this metal, is immersed in 100 gram of water at 11 degrees Celsius. That's quite cold. That means they will exchange heat. Metal will lose heat, water will gain heat, and soon they will achieve thermal equilibrium, and the final temperature is given as 20 degrees Celsius. So that's the final temperature of both the metal as well as water. Calculate the specific heat capacity of the metal. Well, this is the reason why calorimeters are used, to find specific heat capacity of substances. So we start with the principle of calorimetry, which is on the assumption that there is no loss of heat. Heat lost by metal is equal to heat gained by water. That's the opening sentence. Don't forget to write it. That is mc difference in temperature is equal to mc difference in temperature. Remember, for heat lost, it is initial temperature minus final temperature. And for heat gained, it is final temperature minus initial temperature. An easy way to remember is it's always bigger number minus smaller number. Always bigger number minus smaller number, obviously. We can't have negative temperatures involved here. So mass of copper is given. Specific heat capacity of copper is something we have to find out. The temperature decreased by 130 degrees Celsius. Mass of water is given. Specific heat capacity is also given. And in fact, we knew the specific heat capacity of water. Ensure that the units are same here. Yep, this is in gram and this is also joule per gram. So no problem there. And the temperature increased by 9 degrees Celsius. So I've got everything except C1. So this is a normal math problem now. Remove the decimal, reduce it, cut. Final answer is 0.581 or 0.582 joule per gram per Kelvin. If you solve till 4 decimals and then round off, you'll get 0.582. But such a small difference doesn't make any difference as far as accuracy is concerned in exams. So you'll get full marks. Now the 10th sum is very important. We've got water at 50 degrees Celsius, and this time copper is cool at 18 degrees Celsius, and we have to find the final temperature. So the principle used is the same according to principle of calorimetry. Heat lost by water is equal to heat gained by copper. mc difference in temperature is equal to mc difference in temperature, where capital T in both the cases is the final temperature of both, of course, which is what we have to find. Mass of water given, specific heat capacity given. The initial temperature was given, but not the final temperature. Similarly, mass of copper given, specific heat capacity given. Check, are the units same? Yes, everything is in grams, so it's fine. The final temperature we don't know, but the initial temperature we know. So it's an equation with one unknown variable, that is capital T. So again, it's a normal algebra problem. We have to multiply them. We can open the brackets now. Distributive multiplication. Take the like terms together. Number goes here and the T term goes on the RHS. Minus becomes plus. So you get this. I want T alone. So this will go down. You have to divide this. Remove the decimal and actually divide it. You'll get the answer as 47.001 something, but that we can just round off as 47 degrees Celsius. And the assumption, they've asked for the assumption as well, so we have to mention no loss of heat. This sum is IMP simply because of the calculation. Otherwise, the sums are pretty easy in this chapter. It's just that the multiplication and division is quite tough and time consuming, and you may make silly errors in exam unless you practice doing it right now. So don't copy these values. Do it on your own and check the answers, make blunders, learn from them, and that's the way you can achieve perfection in calculation. 12th sum, the temperature of cold water, it rises by 15 degrees Celsius. So we don't know the initial or the final temperature of cold water. All we know is that it rose by 15 degrees Celsius, and that's because it was mixed with hot water, which was initially at 50 degrees Celsius. So again, we don't know the final temperature of hot water. So water in both the cases, according to principle of calorimetry, heat lost by hot water is equal to heat gained by cold water. That is MC, difference in temperature is MC, difference in temperature. Since the material of the substance is same, water, so the specific heat capacity can be cancelled. That will make our calculations easy now. So mass is 300 for hot water, remember. Hot water is 300 and it was cold water which was 600. So be careful while substituting the values. The initial temperature was 50. Final temperature we don't know, and even here we don't know either of them, but we do know that the change in temperature is 15 degrees Celsius. So T minus T2, let me substitute this change in temperature as 15 as mentioned in the question. So the only unknown variable now is the final temperature. So you just solve it and get the value of the final temperature of 20 degrees Celsius for both hot and cold water. This is the final temperature, but they want the initial temperature of the cold water. We know that T minus T2 is 15 because the change in temperature or the rise in temperature was 15 degrees Celsius as given in the question. And here we have found the final temperature to be 20. If the final temperature was 20 and the temperature has actually risen by 15 degrees Celsius, what was the initial temperature then? Well, it was 5 degrees Celsius. And please write the final statement. Therefore, initial temperature of the cold water was 5 degrees Celsius.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.